Hey guys, this is test 55 game 4. This is the Shuttle Van Stops game. It's an incredibly difficult game, so if you had trouble with it, you're certainly not alone. I'll explain it. I've made a diagram here with the 4 stops, 1, 2, 3, and 4. This is of course an ordering game because there is an order in which the shuttle van makes its 4 stops. We have FLMS, the cities, GJRV, the people. Now I've laid out some rules, I'll explain them. We've got L on either 1 or 2, so L//L on 1 and 2. R is still on board when the van reaches Mineola. This means that we could never have R get off before M, therefore we must have M going before M or at the same time as M. So I'm going to put down that M is less than or equal to R because that's the fullest way to exclude the idea that R before M could ever occur, because it certainly cannot. So I put it right there. We also know that J is on board longer than V, meaning that V is before J, so J is never first and V is never last. Then we get to the most difficult, confusing rule of the game that gives lots of people trouble. I'll go through this step by step, little by little. If J is still on board when the van reaches Fundy, meaning that if Fundy occurs before J or at the same time as J, so if F is less than or equal to J, then G is still there when the van reaches Simcoe, meaning that then Simcoe occurs before or equal to G. This is the way to tell us that G does not occur before S is before G or at the same time, so G is still there whenever we get to S. Then we have this otherwise thing here, meaning they are negating this part. They are negating F less than or equal to J, meaning if J is not still on board when the van reaches Fundy. So if we had J occurring before F, then G would not still be there when we got to S, meaning G would occur before S. So that's simply the two parts of this statement. The part in the first 2 lines of the rule, and then the next part here, the second rendition here, is with the word otherwise, everything starting there. Otherwise, again, negated the first line of the rule if J is still there when the van reaches Fundy, meaning negated if J goes before F. So this is the rule as they gave it to us. So we want to take the contrapositive of this just because, well, taking the contrapositive of things is useful. It gives us additional useful information to see the same information but in a different form. So let's start by negating things and reversing. So if G is not before S, what would that be? Well, if G is not before S, then S is before or equal to G. And so if we negate G before S and we get that, then negating J before F and reversing would give us F is less than or equal to J. So we could just write down, S, if S is before or equal to G, then F is less than or equal to J. We could write that down. That is the contrapositive of this statement right here, what is now the middle statement. But why write it down separately when we could just create a double arrow right here? That would be nice, right? That's where it's just a little bit more concise. We actually don't need this part right here. Then if this is double arrowed, then this must be double arrowed as well, because F less than or equal to J leads to S before or equal to G, meaning if S is not less than or equal to G, meaning if G is before S, then F is not less than or equal to J, meaning J before F. So again, instead of writing down G before S, then J before F, we could be a bit more concise here and simply say J before F. So this last rule of the game actually just simply gives us 2 double arrows that look exactly like this, and we'll make use of these over the course of the game whenever appropriate. So question number 19 is a typical orientation question. We're just going to take one rule at a time and apply that rule to all 5 choices looking for violations. So we know, for example, that L's always got to be either 1 or 2, so any choice where it's not 1 or 2 can automatically be eliminated. This gets rid of choice B where we have L on 4. We also know that we have to have V before J. So any choice where V is not before J, meaning J before V, we can eliminate it. That gets rid of choice C where we have J before V. We also know that R can never be before M. M is always less than or equal to R. So any choice where R is before M can automatically be eliminated. This gets rid of choice D where we have R before M. Down to A and E, we haven't made use of this complicated double arrow thing at the bottom here. Let's use that now. looking between the two choices, we see in choice A we've got G before S. So since G is before S, we've got to have J before F, yet we have F before J here. F is with J actually. We need to have J before F specifically, so for that reason, A is gone, leaving E for number 19. Next, number 20, if M is the first stop. So if M is the first stop, that means we're automatically going to have L on 2, because L is always either 1 or 2, and now we have F and S interchangeable on 3 and 4, either F on 3, S on 4, or S on 3, F on 4. Either way, we don't know which. But basically, this is the layout now. We don't know what's happening on the bottom level. But looking at these choices here, they're asking us who could get off first with M. Well, we know J can never be first because V is always before J, so E's out of the running right away. Now looking at the remaining choices, we see that we have R in 3 of them and V in 2 of them. So if we test out V and we can eliminate V and find that V could be first or cannot be first, we'll get rid of 2 choices off the bat. So let's test that out now. So could we have V first? Well, if we can make a diagram where this works, we'll be totally good. So if we put, we could have G before S and J before F, works out perfectly fine. So maybe we'll have, J on 2, we could have G, if J's on 2, we could put F here. If G's on 3, we could have S here. This way we have J before F, G before S, and then we could have R on 4. This works perfectly fine. Therefore, we know it's possible to have V first, and we can eliminate A and B off the bat. So now we're down to C and D. The question is, could we have R on 1? If we could have R on 1, we'll be totally good. So let's put R on 1 and see what happens. If we have R on 1, we could have V on 2, J on 3, G on 4, just as one example. We're living now in this diagram where S is, before or equal to G, and we do have F before or equal to J. Works perfectly fine. We comply with every rule. Therefore, we know it's possible to have R on 1, so C is gone, leaving D is our answer for 20. Next, number 21. If F was first, what could be the order of the passengers? So right away, we know that if F is first, we're going to have L on second due to the fact that L is always first or second. Then we have M and S interchangeable on 3 and 4, the remaining top level slots. We know that, J can't be first and R can't be first due to the fact that R is never before M. We also know that we can't have G first because G's always got it. If F is, on 1, it's before or equal to J. Therefore, S is before or equal to G. So G is going to have to be on either 3 or 4. G actually cannot be even on 2 because then it would be earlier than S. So for that reason, we're going to know that we have to have V on 1. So any choice without V on 1 is automatically gone. That gets rid of both A and B, which lack V on 1. We can get rid of choice C, which has G on 2, due to the fact that G has to be on either 3 or 4. And we also know that we can't have R on 2 because then R would go before M on 3 and 4. Therefore, we know that R is going to be on 3 or 4 as well. So E's gone since it has R on 2, leaving D for number 21. Next, number 22. What happens if G's still there when it reaches L and when it reaches S, assuming it's second? So if G's second and it's still there when it reaches both L and S, we know that L and S are interchangeable on 1 and 2, because if S was coming later, then G would go before it. It wouldn't still be there when it reached S. So if L and S are interchangeable on 1 and 2, then we've got M and F occurring on 3 and 4. We don't know exactly how that's going to play out, but we do know that it's L and S 1 and 2, M and F 3 and 4. We know that we can't have R coming on 1 due to the fact that it can't go before M. We also know that G's not going on 1 because G's already on 2. That leaves V to go on 1 for certain. Then R and J will be on 3 and 4, and where they can or cannot go will depend upon where M and F are. So this is as specific as I really want to get right now. And this will be enough to answer this question since they're asking us what must be true. So must V go there when the van reaches S? No, we could have V on 1, S on 2, meaning that V would have already left when we got to S. So A is gone. Must V be there when it reaches L? No, if L was 2, V would have left already, so B is gone. Must R be there when it reaches S? Yes, because R is on either 3 or 4. S is either 1 or 2. Therefore, R is still there when it reaches S, since S is coming before R. So C is our answer to 22. I will look at D and E, though. Must R be there when the van reaches F? No, not if R was on 3 and F was on 4. So D is gone. And then E, J there when it reaches M. No, we could have J on 3 and M on 4, meaning J would have come before M goes. So J would have already left, so E's gone as well, leaving C. Next, number 23. If G's not there when it reaches S, meaning if G goes before S. So we're looking at the bottom rendition here. If G's before S, then we know J's before F. And we also know that V is always before J, so we could have really added here if we wanted to, V before J before F. So they're asking us what must be false. So 4 of these things could be the case, 1 of them cannot be the case. We've got these 2 different sequences here, both of which are happening. So must be false question, 4 of these things could be the case, 1 cannot. Find the 4 that couldn't eliminate, or if you see something that cannot be the case, of course, just pick it. So G before F, those aren't related. G is still there when it reaches F, meaning F is before or equal to G. We don't know, F and G are not related. J and M not related. R and F not related. V and F though, since G is before S, J is before F, and so since V is before J, V is also now before F. Therefore, D is impossible. We cannot still have V there when it reaches F because V must occur before F. So for that reason, D is impossible and is our answer to 23.